I do research in optimizing energy efficiency of database systems deployed in a cloud environment.
This is Utku Sirin, a PhD candidate of the IC School at EPFL. Utku is optimizing cost and energy consumption of database systems in data centers. But how much is there to optimize? What is the energy consumption of a typical data center?
Tens of megawatts in a large-scale data centers, running all kinds of workloads, it's tens of megawatts. Running only database workload, that's not revealed. This kind of, like Microsoft Azure cloud has a database cloud inside, running only database systems, servers running, but the percentage is not revealed. But we know that for database systems, there are large number of servers that runs only database software. So we know that database software is not running with any other software. It's not like any other software. It's on its own. It has its own set of machines that it is manipulating, but within the ground scale data center, how much is it? That information is not revealed. Not publicly.
Crucially, database workloads have specific properties.
Right, definitely. They are memory intensive. They are heavily memory intensive, right? The CPU load is very low, very low. Most of the time pointer chasing. If not pointer chasing, you're doing some sort of sequential scan. So in that sense, yes, they are running on general purpose Xeon server class processors, but most of the time those processors are underutilized because you don't need many of those features for databases. With a much more power efficient core, you can get more or less the same performance for a database system.
In other words, to optimize database queries, the speed of your CPU will not make much of a difference. The key here is to efficiently manage database workloads and issues such as interferences between concurrent workloads.
In terms of workload consolidation, interference is a very important problem because when you put the workloads into the same machine, they interfere each other. The simplest example is invalidating cache lines.
Let me clarify this a little bit. To prepare for computation over data, it's often useful to first retrieve data from memory into a so-called cache. A cache is a small and fast memory unit near the CPU. The trouble is that if two applications both want to use the same cache, their caching will be interfering, and you don't want that.
Then the average performance of one workload can go lower than if it would have been running alone. This interference, there are fine-grained isolation mechanisms. Intel, for example, provided for last level cache. It provided so-called cache allocation technology, which is kind of a new feature, like a few years it's deployed. And this allows you to isolate, like hardware isolate every core's cache position. It says core 0 is going to access that much of cache, that part. Core 10, access that part of the cache, and you can allocate this dynamically. So based on workload needs, you can allocate the amount of cache per core, and therefore you can put a fine-grained isolation among the workloads.
This is all about making sure these caches are managed as well as possible without interference.
This is a mechanism to use, and then you need to employ a policy for your own workloads. Some workloads, for example, do not suffer from cache misses that much as the other workloads. In that case, for example, you don't need that much caches. This is more workload dependent. So this has been studied for other workloads like Google search. It has been done. But it has not been done for databases. For databases, we are doing it for the first time and trying to see if there is any other pattern that is interesting, that the policy would be changed, unlike say Google search workload. It's more or less transferring knowledge from systems community to database community. There are a lot of works done over there in terms of workload consolidation. It's an old idea, but for databases, it's relatively new because databases typically traditionally run on a single machine. Like one database, one machine. But as I said in the video, it has almost 4% utilization, meaning that if you have 20 cores, you have one core active, rest are idling. So it's energy waste. Then cloud makes a lot of sense, right? Just bring them into put a cluster of machine and bring databases running together on the same machine. But there are interference problems when you do that. And now there are some mechanisms, hardware mechanisms to prevent this. I am not sure if we can completely isolate performance like on the same machine. That is like a research question that we're investigating. But still, we are seeing what are our borders, up to what level we can reduce the interference. So interference is an important effect in terms of workload consolidation.
Also, it's important to note that optimal data management depends on what the applications want to do with this data.
Software prefetching is an important mechanism where you can direct the hardware based on application needs. And software prefetching is important because it heavily depends on the application. application, it's software prefetching. Application decides when to do prefetch. There's hardware prefetching where there's a hard-coded algorithm over there, and this algorithm decides what to prefetch. Software prefetching is at the upper layer, at the application logic layer, so it's more powerful. You can say that bring me this data, I'm gonna use it a few I don't know, milliseconds later, okay? And then it just brings it there. And this is very convenient for the application to use, and particularly for databases, because there are a lot of large number of random data accesses. If you can somehow predict what to prefetch, you can say that, okay, bring these data blocks that I'm gonna need in a while. This can be very useful. So for microarchitecture resource, you basically identify certain features of the microarchitecture, such as large caches or multi-core or software prefetching, and try to use these features at the application layer.
So one crucial aspect of quality data management is to foresee which data will likely be fetched. What are the tools to do so?
Right, so what I do for that is, so one thing is application is already static. For example, if you're doing hash join, if you already know the computation pattern, so you have two tables and you're gonna check equality of two columns of each table, okay? And in this case, you know what you're gonna do. You know what you're gonna do in a while, right? There, you can basically parallelize them by software prefetching because you know the algorithm, how it's gonna process over the data. In case this is studied already in the literature. In fact, from EPFL, there are a few the latest publication is from EPFL.
Okay, that's when you know what you plan to do with the data or what the algorithm plans to do. But that's not the general setting.
So what I am doing is in an unpredictable case where you do not know the computation pattern until you do the computation. The best example for that is B tree search. In a B tree search, in a B plus tree search, to know which node in the next level to go, you need to do the computation in the upper layer. So there I am using a machine learning technique. There I am trying to predict what nodes, given a key, I'm trying to predict what nodes you're gonna traverse, and based on this prediction, which does not have to be the perfect case, but likely to be successful, based on this prediction, then I'm bringing the data blocks to the cache, to the caches, and software prefetching them, and thereby having them ready available in the caches and improving the performance. So my technique is use machine learning, but there can be other techniques.
There are many criticisms of Bitcoin. Some people criticize the loss of energy, which is used by all the computers doing the mining to maintain the Bitcoin network.
What we're going from at this point in the data management community is from static query operators and query optimization algorithms to more and more dynamic ways to process queries. Wait, don't think of how we will optimize this query. Let's first see what the user wants to do, and then we decide how to use the computer's resources.